Hi, I am Clay Hearn with Applied CAX, and I'll be talking today, Consultant Engineer's Guide to STAR-CCM Plus. Just a little bit of background on myself. I've got over 20 years experience in design and simulation, primarily from a research background, focused on, post-power systems, energy storage. I've gotten into alternative fuels, done aerospace, and since I've been with Applied and consulting experience has kind of extracted into a wide range of industries from there. Started off really doing a lot of thermal, doing finite element analysis for thermal fluid systems and structural analysis, got into electromechanics, and then just multi-physics 1D simulations for electric vehicles, hydrogen fuel cell applications. In this presentation, I'm going to talk about a little bit of my life as a consultant. Although I am the primary point of contact for technical support, pre-sale support for STAR-CCM Plus and AIM-Sim products, I really spend about 80–90% of my time working for predictive engineering, doing engineering consulting services. We'll go into kind of what life is like as a consultant, why STAR-CCM Plus is a great fit for us. And then the bulk of the presentation is going to be focused on, my view of workflow and tips and tricks to hopefully you can take up some of these points and improve your overall processes. At the end of the presentation, we will go into a little bit of the project review, some of the projects that we've worked on in the past, and how we've used STAR-CCM Plus to help solve those issues. So I want to start off just kind of a comparison of what I quote unquote, a real engineer versus a consultant like myself. A real engineer, you are working for an organization. You guys have a defined mission, you have a goal, you have a product that you're working for, you have an industry that you're focused in. As a consultant, we are somewhat out there in the wild. We are working with clients that come from a wide range of industries. We have done aerospace, but we've also done medical. We've done building services. It may be wastewater treatment, or it may just be kind of a structural, basic mechanical analysis. One aspect of working for an organization, you probably end up doing the same type of analysis quite a bit, or same groups of analyses quite a bit, and you will become an expert in doing that type of analysis. For us as consultants, we have to be a little bit more of a generalist. We have to be very good at a wide range of analyses and very competent, and that's because, going back to the first point, we have a wide range of clients coming at us from many different industries. Another aspect is, working in an organization, you have a set tools and set processes that you use, and namely here, it's a CAD tool. So your company's purchased, say NX for CAD. Most of your models will be coming to you, say, from NX. It's easy to link to those models. Us on the other end, we have to be flexible. So, our clients, they could be using Inventor, SolidWorks, Solid Edge, or Creo, or some other CAD tool. Sometimes we're doing a lot of work with building services, and they're using Revit. So we've got to look at ways to get those models in a neutral format that we can use. Sometimes we're completely unlucky, and we end up getting 2D drawings that we have to build up a model from scratch, or even just a sketch. The last aspect that's the biggest difference, I would say, is the duration of your projects. You'll be working on a project going from birth, development, all the way to deployment. That process could take 3, 4, 5 years. You're going through many different iterations and design concepts. We're basically passing by. Typical project length is maybe 2 to 6 weeks. Usually what we're looking at is a client is coming to us and saying, hey, we've got this design. We want to improve the flow of the design. So we'll look at the baseline concept. We have to evaluate some design considerations, and then it's gone. Never be saw again. So considering all those, why is STAR-CCM Plus a great choice? First off, we have a ability flexible import of CAD. And what we'll also talk about is we take advantage of the built-in CAD client. We have an automated workflow in STAR-CCM Plus. So this again goes back to, typically the overall project setup. We're getting into baseline design. We have to analyze that baseline design, see how it's working, and then quickly apply some changes to the design to find an appropriate solution for our client. We got a multi-physics capability. Our projects, again, they could be coming from all different industries. We could do something as simple as, just a standard flow that you could analyze with a constant density gas or constant density fluid, or we might be doing, a multi-physics analysis where we're using Lagrangian particles for combustion. And then again, scalability, cloud computing. With CFD, your models can easily get quite large, 10, 20, 30, 50 million cells. We do have in-house computers. Since we are focused on quicker turnaround, we do try to keep our models somewhat on the smaller end. We have resources to run solutions up to about 48 cores, but we've had projects where, we got to go beyond that. And that's where we'll take advantage of cloud computing resources, such as AWS. So now I want to get into some of the workflow and processes that personally I use in STAR-CCM Plus. So the overall layout of the workflow is, hopefully we receive CAD geometry from the client. Like I said, sometimes it's just a sketch. Sometimes, depending on the model, we might do what I call some external processing of it, pre-processing. So, and that could be done in NX. This is basically if we get a model that's overly gigantic, which sometimes we do, I will bring that into NX and kind of whittle it down and at least throw out everything and kind of get to the section that I'm focused on, and I export that out as a parasolid. But primarily to me, my work is starting when I can get that model into STAR-CCM Plus, and I always directly go into the CAD client. And I'll show you some reasons for this. The CAD client, in my opinion, is one of the very strong features for STAR-CCM Plus. You've got a direct link to geometry, to mesh, and that's where you can easily make changes, influence the model, and influence your analysis. After the CAD client, after you've done your fixing of the geometry and you've applied your changes, hopefully you've taken advantage of parameterization that I will talk about. You can bring that into the parts menu and define your mesh pipeline. We define our physics, continuum, interfaces. Won't talk too much about this here, as this is pretty well dependent about the problem, the application, and what industry that we're focusing on. Of course, you do your analysis. And then kind of following up the discussion from earlier, we get into post-processing, and this becomes a very important part where we have to put our results in our report. Our primary, as consultant, the primary deliverable we have is an written engineering report. This is going to our client. In addition to making sure that it's a technically sound report, we have to clearly detail, the results of the simulation to the client, and keeping in mind that that client may not be a very technical person. So on this slide, I want to kind of go a little bit over the CAD client. How many STAR users are here? We got 1, 2, 3. How many fully use the CAD client as much as possible? Never. I mean, To me, it's a very strong feature. So we got an example. I mean, the CAD client in STAR-CCM Plus, it is a full 3D feature-based parametric modeler. It is basically a lightweight version of, say, IMAX or SolidWorks or something like that. For dealing with, you know, if you're dealing with a natural assembly, it's definitely not good enough for that. But if you're dealing with a CFD model that you're already going to want idealized, it is more than powerful for that. So we can use it for creating initial geometry, going back to if we have drawings that are provided to us, or taking in geometry that we're looking at and adding some features or doing cleanup. So an example I have here is kind of a little T-pipe that could be used as a static mixer. And in here, in this quick example, we want to add some static vanes to it that we could use as a static mixer. So like any feature-based CAD program, we'll start off grabbing a plane. We can start with a sketch. And just like any program, we start adding our baseline entities. Here they could be, you know, squares, circles, arcs. On these entities, we can add geometric relations to define the sketch. In addition, also add in our dimensions for this sketch. And here we're sketching out what would be a single mixer blade. So we've got the thickness. Once we finish the sketch, we add an extrude operation to get a body part, and then we can add an additional operation to revolve this body part into a number of mixing vanes. And everything that we did there, you know, going to the dimensions that we've added to the part, the thickness, the length of the blades, the angle of the blades, the number of revolutions of the blades, those are all numbers that can be brought out and used as parameters for study. And once you've, you know, if you were to do that, you know, your parameters come out below here. They're live that you can update. You can change that parameter, hit update model. It automatically updates the model. When that's connected to your mesh, you update your mesh and perform your next analysis. Another feature is being able to use geometry cleanup within the CAD client. So this is an example that we've did analysis on a few years ago, where we basically have a flow manifold. There's a number of bolts and washers on it. I don't care about the bolts and washers. You could go through and try to click each of those and find them and delete them, but there's better and faster ways taking advantage of the filters within the CAD client. So first here, we want to create a part filter. So we'll go to the filter menu, we'll select all the nuts, bolts, washers that we want. It will identify all those components within the assembly. And then we can go to that filter feature and right click on it to delete all those parts. In the next step, we may also use a defeature process within the CAD client to take out, you know, small features such as radii or holes or chamfers. Again, on doing this, we can basically go to the part, right click on it, bring up the defeature tool, automatic defeature tool, where we select the dimensions of the fillets and radii and whatnot that we want to delete. It removes that automatically. In some cases, we might have specific faces that we want to get rid of. So in that, we go to defeature faces and then just automatically select all those faces that we want in order to simplify the geometry.
And this is all CAD geometry.
Yeah, this is all CAD geometry. And then on here, this is taking advantage of the let's see if I can go back here without breaking it. This is also combining what we did beforehand with the filtering tool. So we can identify, say, all these faces that were the countersinks for those bowls, and it will create a filter of all those faces. And again, we can just defeature those faces. So there's lots of possibilities here and tools to use in order to clean up your geometry directly within the STAR-CCM Plus CAD. I do usually end up with a geometry checklist that I want to go through, like make sure I have a clean geometry to go into a mesh. And what I want to make sure is that, you know, I don't have any small little sliver of volumes that, yeah, you go through, you try to mesh this, and you got face validities of 0.5 or 0.6. You run those are just automatically going to blow up your simulation. I will extensively use the extend faces tool within STAR-CCM, within the CAD client, make sure that I've got clean contacting faces. I don't have any small gaps. Again, we reduce the geometry complexity and take use of the Boolean operations for CAD, subtract, and add. Another item that I want to diligently do with the parts is to take advantage of naming the faces. So you can basically go to any face on your part, right click on it and rename that face, and that name will get populated down here instead of the default face that's normally named. You know, you want to do this for your inflow conditions, outflow conditions, you know, any other surfaces that you might be having a contact with or another boundary condition is applied to. Also, to do this to any faces that you're going to want to apply a particular mesh to it too. And lastly, in my geometry checklist is take advantage of parameterizations. You know, as I said, we're going to usually most of our studies are quick turnaround. You know, we have to make changes. You know, we got to take advantage as much parameterization as possible. You know, as I mentioned before, when you're drawing out your sketch, yeah, or another feature, you can expose that parameter, but it becomes a parameter under the CAD menu, which you still have access to change in any type of design studies or design managers. I typically prefer to keep everything as a global parameter. So under the main menu, the tree, there is a parameters menu. You can define those global parameters and still use those to drive dimensions or even features in the CAD client. The one thing that you do have to be a little aware of is that it doesn't automatically pop up into a menu as you type it, so you may have to force in the format of the $, squirrely brackets, and the parameter name. One of the advantages of using the parameters here in this method is that they can go into driving a larger equation or feature. So, you know, an example here is, you know, setting up a chamfer between two varying diameters. After we've finished the setting up our CAD geometry, you know, we bring that over finally into the analysis side of STAR under the parts menu, and this is an important step where you basically build up your meshing pipeline. And this is another key feature of making sure that you have parameterized and automated workflow. You know, still with the clean geometry you have, you might be doing, you know, a volume extraction, you might be doing a transform operation. You know, if you're looking at air drag over a vehicle, you can use a transform to basically change the angle that your vehicle is at for drag at different levels of attack. And that transform operation can be driven by, you know, a parameter that you basically just update and, you know, regenerates the mesh.
Quick question.
Yep.
How well does STAR-CCM CAD handle changes from incoming geometry? Right, so imagine look up that solid out.
Yeah. I've done that. Basically, you know, you create, the question is, how does the CAD tool handle changes from incoming geometry? It can do it fairly well. So you will have a feature on there that is your import part. So you would have to go back up to that import part, somewhat in a rollback state, and, you know, re-import the part, you know, point to the new file that you're looking at. It will try to go through and match the faces. Depending on, you know, the complexity and the changes you've made, sometimes it does that job pretty good. Sometimes I've noticed, like, okay, I just ignore the faces, delete all the new ones, bring the new ones in. And, you know, sometimes I've had pretty good luck being able to rebuild something that was complicated. But yeah, once you get here, you define your meshing pipeline. One thing I'm going to point out in this, it's a very important operation, is the imprinting operation. Primarily, we do this for identifying contacts. You know, if you've got a conjugate heat transfer analysis, you've got, you know, your fluid volume contacting your solid volume, or, different solids contacting each other. It's very important that you have this imprint operation, or at least a contact operation here. Have this little slide on here right now because I will get throughout the year 2 or 3 support calls asking me a question saying, either they're having a meshing issue where they're getting this message saying that they're overlapping surfaces or a piercing surface, or they're running their analysis, they're not seeing any heat transfer across a boundary like they would expect to see it. And the answer is always kind of, well, did you put an imprint operation in there? No. So what imprinting does is typically, your CAD geometry is coming in with a set tessellation. You are, finding those 2 contacts, those 2 mating surfaces, retessellating it. And I will typically do this, when I'm first bringing in the parts, I will imprint everything together, and then I will actually assign those parts to the regions. When I do that, any parts that we're contacting, it automatically creates those boundaries for me, and I don't have to worry about that. And ideally, if you do take advantage of the polyhedral mesh, and you can get a congruent mesh across the boundary, which is really what your ideal is. So you don't have to worry about any numerical errors from interpolation of results across that. But this overall process also helps any meshing issues that you've had. I have run into very sticky cases where I've had a meshing issue. I've added my imprint in the mesh pipeline operations, still getting a meshing issue of overlapping faces. If you go back into the CAD, there is a CAD imprint on the CAD side. So I've employed that, and that's also been a feature that's been able to solve some of my headaches. Getting into the surface repair toolkit, I think this kind of gets onto an earlier question. If you're so bold, or you have such a horrible geometry that's not a CAD-based geometry that you bring into STAR, if you have issues with that, there is a surface repair toolkit that you can use. In that surface repair toolkit, you'll be going directly into the tessellations, and you can basically rebuild the tessellations if you need to. I stay away from this because I personally prefer to stay in CAD as much as possible. I will use this as a diagnostics tool though. So again, especially if I've had an assembly with many different components on it, I try to mesh it and I come up with an error of overlapping faces, I'll go into the surface repair toolkit. And one thing with the surface repair toolkit is you can look at the different stages through that meshing pipeline, either the original geometry or maybe you did an imprint operation or something else, or the surface mesh, and see what the surface tessellations are and start identifying where your issue is. Now once I've found out my issue, I will usually go back to the CAD model and try to fix my remedy there. Why I do that is because once you've made changes with the surface repair toolkit, you've basically broken your automated flow. That meshing pipeline you have, the nice automated flow to be able to change the number, remesh, get a solution, that's completely broken. But there are going to be some situations if you're dealing with STL files or non-CAD files where this is going to be the only fix you have. I want to move a little bit now into more workflow that I do for automation. One of the key practices that I have is setting up my parameters here. And the parameters will be all my flow conditions, boundary, pressures, heat loads, etc., in addition to any geometric boundaries I have. I might have a model where I've got 3 or 4 inlet ducts that each have their own inlet mass flow rate defined, or maybe it's the same mass flow in rate defined. I don't want to sit there and hunt through that regions and the boundaries within the regions and try to find all those and make sure that they're cleanly updated. This leads to the class 1 errors. So if I keep everything under parameters, I just go to the parameters, I can update these values. These values can also end up being functions and calculations of one another's too. One thing I will point out in the newest release of STAR, well, not the newest release, the 2310 release of STAR, I'm not sure if 2402 has come out yet. They've created an automation node. So this is basically to help you reduce the amount of scrolling you have to do up and down on this menu tree. So all these folders for parameters, field functions, simulation operations, they're now more tightly located here under a new automation node. And it should hopefully help your overall workflow. Another feature that came out in 2310, which I'm excited to use, although I haven't had a project to use it on, is stages. With stages, you can essentially, set up 2 or 3 different physics models in your simulation and have the simulation automatically switch between these physics models. Maybe you were using a macro before, but this is just another way to kind of help out with that automation. The best application is doing transient analyses for these right now. So you could have two sets of physics set up, one for steady state analysis, one for transient analysis. If you're doing a transient analysis simulation, the first thing you have to do is run a steady state model to at least know what your input conditions are. What's your input flow? What's your input temperature distribution? You may run that as one simulation file, save those results out, and then pick up those results to run in your transient case. Now this can all be set up under one simulation and automatically switch between those two physics and time domains. Parallelization and GPU acceleration. This is a feature that's ongoing development from with Siemens to enable more GPU acceleration with the different solvers in STAR-CCM Plus. It is somewhat of a long process because essentially they have to go through and reprogram the solver, each solver for running on GPU. As you're looking at new releases coming out, you'll see under the release notes, what functions that they've added for GPU acceleration. You can see here in this plot, if we didn't have this bar here, there's a huge amount of decrease in time running GPU, up to about 1/5 of the time compared to a normal CPU. And you can also realize that as an energy savings too, if you want to track the greenness of the simulation. The latest release of STAR that might be interesting to people here in the audience is that they've now added the coupled energy flow solver and then the native equilibrium air equations in 2310 to GPU solutions. So this basically enables running models for hypersonics in STAR-CCM Plus. Last couple of slides in this section, we'll move into post-processing. As I mentioned, we do engineering reports. That's our main deliverable to our customer. Yes, the engineering report documents everything that you did in the analysis, but you also have to document the results. Really, our customers only care about the results. So the results in CFD, they're going to be, plots and images. You got to make sure that they are readable and that a person who may not be a technical person can understand this. First thing I suggest starting out is going into the tools, options, visualizations, and you can set up a couple different, default functions here so that you don't ever have to worry about it. One's the color bar that I'll talk about later. The next is on the plot. For some reason, the plot text on default STAR is just way too small. You can't read it. If you put that in a report, if an engineer put that in a report, I would slap them because there's no way that you can read that. I suggest you go in here, go to default plot options, increase your font size. You can increase the line size, the line thickness. So if you do carry over, 2D, XY plots, histograms, they're clear, readable for your reports. Next, I would say is looking at, I got rid of it. Looking at your color maps. Again, I kind of think the default color map that they give you in STAR, it's good for seeing, the high and low ends, but you miss out some of that middle, what's going on in the middle temperature range as we see here. I have really moved to using either these white-red color maps that have a lot more contrast so that I can pick up a little bit better of the differences, say, what's happening, not so much as the extremely hot part, but, not so hot, cooling off part. We can see these a little bit better than just kind of a blanked orange, washed out green. And then you should also, play around with either if you're going to have your plot set up as a linear scale or a logarithmic scale. For us, we do a lot of simulations that I would say are, building flow or enclosure flow. So you've got air vents that may be delivering air at higher velocities into a larger enclosure or room, so around 10, 12 meters per second, but the airflow in the rest of the room is going to be fairly small. So if you look at these two enclosures, same result map, on the left with a linear scale, the default, we see the high velocity air coming into the room, but everything else basically looks like it's zero. There's no flow. If we switch that over to logarithmic scale, yeah, we see the high velocity coming in, but we do now see a little bit better understanding of, okay, we do have, a little bit more flow around these areas, 1, 2 meters per second, and we can really identify where the actual no flow areas are occurring. And lastly is animations and screenplays. We do have on our website for Applied a little video on how to set these up. These can be pretty fun to set up if you've got a number of different plots and streamlines and views within a scene. You can animate through all these different scenes and put together a much larger video. Really, the greatest impact of this is more or less for marketing. If you're going to be meeting with chief engineers and the chief engineer is your boss and you want to show off your simulation, this is a great tool to use for that.
And I'll say, I didn't want a lot of play because he worked. So yeah, they grab all of it, make it. It's really cool way.
All right. Yeah, I got a few slides here that get into some of the projects that we've done in the past. One's on boiler combustion. This has been a good partnership with a local company in the Portland area, SHB Power Plant. They focus on retrofitting power boilers and recovery boilers, primarily in the paper industry. We do the CFD modeling for them to analyze baseline cases and then evaluate changes that they make. These are very nasty, complex models. We are actually taking advantage of the coal combustion model in STAR-CCM Plus. The simulations basically start off where they're injecting a black liquor fuel towards the bottom of the furnace. We capture the drying, devolatilization, tar burning reaction, ash remains throughout that entire combustion process to understand what the resulting flow is, heat distribution, and try to get some idea of what the emissions could be. One of the challenges for this is that we can get a chemical composition of the fuel that they're using, but we don't have any idea of what the actual combustion reactions are that are occurring. That data just doesn't exist, and mills don't have the money to go through and do detailed tests on those. So we take advantage of a complex chemistry solver, relaxed chemical equilibrium. We can name a number of species that we know are going to be general species within the combustion process, and without knowing anything about what's actually happened, we are able to locate, get a good idea of where the flame position is going to be and the overall heat release. Again, we try to keep these low cell, and it depends on the size of the boiler. I mean, down below it might be, say, they call this the bowl nose. Try to keep this below 10 million cells, but it gets up higher as we go up through different platens, and it depends on the design of the boiler that you're looking at. So they can get up to maybe another 20 million cells. I mostly run these either on in-house computer with 48 cores, and I'll run for a week. I have taken these up to AWS, 96 cores, and yeah, that's significant improvement getting down to, a few days, a couple days. Another fun project we did was a flood barrier. This actually started off as a simple hydrostatic analysis. Small company that was interested in putting out low-cost aluminum extruded barriers, wanted to understand, maximum width, height that they could design their barriers for. We did a number of studies for them, hydrostatic pressure, gave them their answers. They came back and said, well, we have this requirement that it has to withstand flow at a certain velocity. So we thought this would be just a fun project to put a cool video together of just using the VOF model, actually have it smack into the barrier. If you take those pressures, map that back to the finite element mesh that we have, and reevaluate their design. In this analysis, we're actually taking advantage, with the VOF model, using adaptive mesh refinement. So adaptively, it is going through and refining the mesh at where the interface is between the air and the water. This, is probably a very applicable tool for many people in this room doing the adaptive mesh refinement. Again, I have another quick video on the Applied website that shows how to set this up. Great applications for using this technique in, supersonic or hypersonic applications where you don't want to just completely over mesh the entire simulation. You can just let it find out where that shock barrier is and locally refine the mesh there. And finally, again, we've done motor cooling. This was for electric motor for VTOL application. Lots of conjugate heat transfer happening in here. We started off the project doing some simple design manager experiments, looking at, thin size, width, length, thin spacing for them, and then feeding that to the next level design where we looked at the system model, capturing airflow over the exterior of the motor. We've got the winding heating, core losses on the stator side. We have power electronics on the rear side that are soaking in, hopefully soaking heat out through the fins to the passing air. And then also on the inside, we have the motor. We've got, in this application, rotating reference frames that we're considering to consider the air movement inside from the rotor movement, and then also the rotor heating itself, permanent magnet, core losses, and eddy current heating in the aluminum hub. So that's basically kind of a summary of the simulation of the overall workflow that we use. Again, we're taking everything that the client provides to us. Hopefully the client is providing us information with a neutral CAD format that we can put into the CAD side of STAR, start building the simulation with a clean geometry and taking advantage of the automation features within STAR-CCM Plus for design studies.